Hello everyone, welcome to the channel and I hope everyone is doing good. So in today's video, we are going to look into alternative of vector database. We are going to discuss about the page index. We'll look into the concept in details. So I would recommend people first to understand what is RAG pipeline, either from my videos or from any of the blog. So first you will have the understanding of RAG pipeline, then you can understand this video or you can relate this video in a more meaningful and more relevant ways. So if you're new to the channel, please subscribe to the channel and do spread the video and the channel to your friends and colleagues who want to upskill themselves into a data engineering skills and want to get into the Gen AI, which is very much relevant to the data engineering skills. So you can see here I have created one flow diagram for the RAG. So in just less than 1 minute, we'll revise that what is RAG pipeline and what are the component. So we have the input document. I have written here docs. We do the chunking of docs. We break the docs into small parts. We create an embedding on the top of that chunkings, assigning the numbers to that chunkings and storing that into multidimensional vector in a vector database like ChromaDB, Pinecone, any of the vector database. Then with the help of SQL, user input SQL, we do the retrieval. We fire that into the vector database and do the retrieval of the chunks and the documents. And that chunks or the retrieval chunks is passed to the LLM, which gives you the final result. So this is the normal pipeline of a RAG when we use a vector DB. Now we'll understand if we remove vector DB, if we remove embedding, then what is the alternative? How we can improve and what was the problem in the RAG pipeline during the retrieval process? Before understanding what is page index and where it lies in the pipeline, first we'll understand, like we have already seen in a brief, like what is RAG pipeline. So what is the problem in this pipeline? So in RAG pipeline, we do chunkings, we do embeddings and put into the vector database. So this chunking size is the biggest problem in the RAG pipeline. Now, if you give a bigger chunking size, then the retrieval will be very slow. If you give a small chunking size, retrieval will be fast, but there are chances of losing some important information. Why it is so? Like for example, chunk 1 contains some information about the Spark EMR. You have asked questions something related to Spark EMR. So chunk 1 contains Spark EMR questions, and chunk 2 contains something about optimization of the server. Both are actually related, but sometimes you may lose the information of chunk 2. So there is an option of overlay also in the chunking, which we have seen in our previous video. But still, chunking is a one of the bigger problem. If your document is a very big size, then divided into small chunks is a problematic situation. The second thing is creating embedding and into the vector database. So embedding helps you to give the more semantically correct answers. But sometimes that some answers seems to be semantic for a human, but that may not be semantic to the RAG system. Why so? Because in the RAG system, the two words or two sentences are semantically near or correct is understood by looking into the embedding number, by looking into the vector number of that particular two chunks. So there are chances of losing the context, losing the semantical meaning into the answer. There are chances of losing the complete information because of the chunk sizes into our information. This process is also CPU intensive because, for example, you have very large document, multiple documents, and you are creating an embedding and creating an index out of it into a vector database, creating an index metadata. So retrieval is very much difficult because the retrieval process will look into all the chunks and find the similar number into it to create a meaningful answer. So it's a kind of looking into multiple chunks before giving that output to the LLM. To address this problem, there is a concept called page index has come. So page index is not a new concept. It was there in the open search, in the previous multiple kind of searches we used to do page index, where we divide the document into different pages. So if you're from a big data background, so you would have understood about the partition, hive partition. So what happens in the partition? We create a bigger directory. Inside that, we create a multiple small directory. For example, year is a bigger partition. Inside that, you can create different partition on the month wise. So one bigger directory will contain small directories. And if you want to search on particular year, particular month, then there will not be happening a full table scan or full data scan. It will only scan that particular folder. The same thing which we are going to achieve by doing the page index. We will not doing the scanning of full document. We will be scanning that particular number of pages which contains that index or which contains the keyword. Fine. So this removes your vector DB concept. It removes the embedding concept. It removes the chunking concept. This doesn't mean that chunking, embedding, and vector DB combining thing is irrelevant nowadays. It's not irrelevant. It is useful for some specific use case. Page index is useful for some other specific use case. We will understand that which use case the page index will be more beneficial and where the embedding things will be more beneficial. That we will see in the last portion of this video. So now we'll understand how this page index comes into this picture. So you have the documents. Now that documents is divided into pages, right? Then that tokenization happens of that pages, that words are extracted. Then we create the index of that tokenizer word. We create the relationship between the page and tokenizer here. And then here is the retrieval process. So retrieval happens with the help of index and tokenizer. So here also the same kind of arrow will go from document to pages to tokenization, then creating the index, means relation between the pages and index, and then retrieval happens. And then let's copy this box. We have LLM, right? So retrieval gives it gets the answer, then it gets into LLM. The same way here also retrieval happens from here to here. It gets the answer, it gives to you. Right. So here you see you have chunking, embedding in the vector data. This has been we have removed this with the help of page index. Page index, we create a page, we create a tokenization, we create an index. We'll see in the detail. Now we'll see that we have seen that what was the problem in the RAG by using this method. Use case wise, we'll see in the last portion of this video. Now you'll understand how these particular things work. Just clear the concept, have a good concept, like how you have had a good concept to the RAG pipeline with the help of vector database. Now create a very good concept with the help of page index. Then you'll be then you'll be able to understand that where to use which kind of pipeline. And wherever you are seeing that vector database is dead or vector database is of no use, that is not correct. Everything is use case specific. Some use case will use the traditional way of approaching to the answer. Some use case will use the advanced AI multi-agent way of reaching the answer. But the whole purpose is to accomplish the goal, and which is the correct and which is the efficient path we have to take it. So nothing is wrong or nothing is correct. It depends on the use case. So now we'll see the detail of the page index. So as we have discussed, like first there will be document. So this is the document EMR underscore serverless guide. One PDF is there. Okay. So there are multiple pages inside that PDF. So first thing is doing the paging part, means we divide into different pages. So page one, maybe the chunk of 2-3 pages, maybe the chunk of some documents inside this PDF. So we first divide into different pages. Each page becomes an object. Like if I want to retrieve page number 2, page underscore 2, I can get it as an object. Fine. Then after doing the page, we tokenize it. For example, in one of the pages, you have this detail. Spark optimization includes adaptive query execution, dynamic allocation, and memory tuning. Now from this sentence, token is extracted. Tokens are the words like Spark, optimization, then includes may not be one of the token, adaptive. So the tokenization method understand or the library which will be using will understand that what are the keywords into it, what are the tokens. So these tokens are created or taken out of this text. And then we create an index. We'll see how we create an index. Now we create an index of this token and the page. Our third step is tokenization. So we create an index of the page and the token which we have extracted. So we use inverted index. Why inverted index? I'll make you understand. Before that, you understand like what kind of index we are creating. So one keyword was Spark. Okay, so I'll do one thing. Just copy this. So one token was Spark. So Spark is available in what all pages which we have divided. So it contains in page 3. Then optimization is in page 3. Memory is in page 3. Adaptive in page 3, page 5. After with this help, we create the index like Spark is in 3, 4, 6. This is imaginary number I have taken. Adaptive is in page 5. Serverless in 1 to 6 page. So now we have created the index of the token and the page number. So why we call it an inverted index? Because generally if we have to create an index, we can have the page and then what are the tokens inside it. But here we are doing the opposite. We are writing the token first and then in the index number, searchable number, we are putting there the page number. So we call it an inverted index. Now we'll see how we retrieve out of it. That is most important. Fine. And I'm seeing that it has simplified the process what we used to do in a traditional RAG, but still everything depends on the use case. Now how the retrieval process happen? The user has the query, how does EMR serverless improve Spark performance? Now again the token is taken out of it, like EMR serverless Spark and performance, and then searching is done, like in which all pages EMR was there. So we have already created an index. So with the help of index, it will search where is the EMR. So EMR is into 2, 5, 10 pages, serverless is in 2, 8, 10. So we'll find out in which all pages this particular token is there with the help of index what we have created previously. Now this page number 10 is common in all the keywords, all the token. So we'll consider 10 as the highest ranking page number in the rank wise. Similarly, we'll get another pages like page number 8 is in 3 of the common index. So page number 8 will be ranking 2. So similarly, we'll have multiple pages retrieved with this information, and then we'll have the set of pages and that need to pass to LLM. But before passing this all the pages to the LLM, we have to find out what is more relevant. Like for example, you have got 20 pages, so you cannot send 20 pages to LLM. Technically you can send, but if you send these many pages to LLM, then LLM will confuse in getting the answer, and there the hallucination and the or the wrong answers will be delivered by the LLM. So in that case, after this process, after getting all the page number, we do the ranking, we do the re-ranking what we have seen previously. The similar kind of thing we do here to get the most relevant pages out of this process. We'll see how that is done. So one of the algorithm which we use for the ranking is BM25 because BM25 because in this the keyword frequency, how many times a particular keyword has come or particular pages has come, what is the length of the document, what is the keyword rarity, all these things are taken into consideration before giving the higher rank to any of the pages. We'll go into detail of this algorithm in the in maybe in the next video. But to understand, a ranking needs to be performed. So what we are doing, are having a PDF. We are dividing into different pages. Then ranking. Then we get out that take the token out of each of the content of the pages. We create an index, inverted index. Then the user fires the query. We get the keyword out of the user query. That keyword is searched in the index to get all the relevant pages. We do the ranking to get the, like in all these pages we have to find the top 5 top 10 documents, so that all ranking is done. And after the ranking, for example, we have got the top 3 top 3 pages, so that all top 3 pages is passed to LLM to create a response out of it. See, if you open any chat GPT, you can give a normal PDF. You can upload a PDF to the chat GPT. You can ask the question. It will try to get an answer from that PDF if you give the proper prompt. Same thing which we are going to do here. First, we have to identify, like in ChatGPT, we are manually uploading the PDF. We know that we want the information from this PDF. Here, we don't know from which document we want to have the, or which portion of the document we will have that information. So we are doing all this process to identify the relevant pages, and that pages is passed to the LLM with the user question, and then LLM use its intelligence and try to find out the answer from that document. So if your document relevance is at higher level, that means your LLM answer will be also at a very good and accurate level. I hope you understand. You would have understood how this process works. This is very fairly simple. And in the next video, maybe I'll come up with the practicals of it, with the code of it. Now we'll see the very important part, in which use case the traditional RAG with the vector database RAG is relevant, and in which use case this particular page index retrieval is relevant. We'll see. So now, first we'll understand where the page index will be more relevant. Now, a simple rule. If you want the retrieval to be exact what the answer should be, or your answer should be the exact same kind of word, same kind of meaning, then we have to go for a page index. Like for example, in the legal document, if you have 5,000 contracts and pages, you have a query like so termination clause. So you know that the output is in 48 number page, 95 or 120, or this is the output which is given by the retrieval process of the RAG. So in this case, we need the exact word matches. We don't need the semantic meaning. So we need exact keywords. So in the page index, exact keyword is matched because the index is created of the exact keyword and the number of pages what we have divided. So exact keyword matters, and where the high explainability is there, like you can get more details because we are getting the full page out of it. It is not just a chunk, it's a page. Same thing for the insurance document. Here also we need the exact. We cannot go on the guesswork. We cannot go on a semantic meaning. We need an exact word match. So in this case, we will have the page index. Now, where the page index is not useful, for example, you fired the query, what are the optimization way of EMR serverless? So in that we don't want the exact keyword match. We don't want the exact factual answer. We need something which will give you more explanation on the optimization process. That can be optimization process, that can be optimization examples, that can be optimization benchmark. So all these answers can be included in your final answer. So in that case, we will not use page index. We'll use the vector database, because vector database will find out the similar meaning of your query, and page index will find out the exact meaning of your query. Okay, if you want an exact match, go for page index. If you don't want an exact match, you want a semantic meaning, then you go for the vector database. This is very clear. Now we'll see the difference of it. A simplified comparison between page index and vector DB. So exact keyword search is very good in page index because it does the exact keyword search. Vector DB moderate. If you get the exact keyword, it's fine. If you didn't get, then also it will give you the output. Semantic understanding is very poor in page index because page index we don't have the any concept of understanding it semantically. But in vector DB we have an embedding concept which gives you the semantic understanding. So that's an excellent. Anything where you need an explanation kind of information, there the vector DB will be excelling. Version each search is excellent. Then we come to the cost. Page index cost is low because we don't need any vector database. The searching is not a full scan search, so your CPU consumption is less. But in vector DB, it's higher because if you have a huge amount of data, that chunking will have that CPU. Embedding is very CPU intensive, and then you have to put it into multidimensional into vector database, do the searching in the multidimensional, and that is very CPU consuming process. Infrastructure also, page index is simple. We don't need any vector database something, but in vector DB it's a complex. These are the LLM required. In page index there cannot be if you're doing the exact search low. So without LLM also you can get the exact answer, but in vector DB we need LLM to combine the semantic meaning to give you the exact near to answer. The final take, page index is not a replacement for vector database. This should be very much clear now. Now don't go to that kind of document where it says that vector database is dead or vector database of no use. It doesn't make any sense. So it all depends on the use cases I have told you. So page index is not a replacement of vector database. So page index when you need an exact search expert, vector DB when you need a semantic search expert. Now, for example, if the user searches for EMR version this, shuffle partition, error code 404, claim ID, the exact search it uses. So page index is often superior here. If user asks, how can I improve this part performance? What reduces job startup time? How do I optimize cost? So here we need an explanation kind of answer. So here vector search is more superior, because if you ask this kind of question in a page index, the exact search will give you the limited answer. It will not give you the explanation of it. So each things has a different use case, and I'm happy that we have a page index now. Page index is an old concept. Everyone would be using it in different technology, but in the RAG pipeline, it came as a new concept. So earlier, everything has to be done by the vector DB, but now this page index has created a new way. Now there is one of the big advantage of page index will come into the future. What I see here is page index. There is a hierarchy, like one page, another page, document, then page. If you have a very large document which is related to each other, there this hierarchy will increase, and then the searching will go to a very, like, searching will be again CPU intensive. I hope by that time you will have another way of doing the searching in the RAG pipeline. I hope this video would be beneficial to you. If you like this video, then please click on the like button. Post your question in the comment. If you like the video, you want to post something good about the video, you can post it in the comment. If you want to connect me, you can connect me through LinkedIn. You can go to my channel pages, and there is a LinkedIn link for my profile. Any kind of question of DE and GenAI, you can place it in any of the videos comment. I'll just go through it, and whenever I feel like answering to that questions, I'll answer it. We'll meet in the next video. Till then, happy learning and goodbye.